So now it's clear that minimum number of inversions possible with n distinct elements is 0. Maximum number of inversions possible is n into n minus 1 by 2. And average number of inversions it is n into n minus 1 by 4. Now again look at the algorithm, insertion sort algorithm. So what happens in insertion sort whenever this condition is true? Here we remove one inversion. One inversion is removed. One inversion is removed. So in the sorted order output, that is sorted order, what is number of inversions? Number of inversions is 0. Only inversions have role in which step of this algorithm? Which step of this algorithm, insertion sort algorithm? Which step of this insertion sort algorithm is affected by the inversions?
When this fourth condition,
only fourth step. Other steps, first step, second step, third step, they okay, no, there is no relation between inversions and these steps. No, how many times they are repeated. Even seventh step also there is no relation. Only 4, 5, and 6. Here it's a problem. Is that correct? Is that correct? Is that correct? Okay. Now minimum number of inversions case we consider. Minimum number of inversions. In that case, that is 0. Number of inversions is 0. In that case, how many times step 4 is repeated? How many times step 4 is, that is comparison operation given in step 4 is performed? How many times this operation is performed?
n into n minus.
How many times this operation is performed?
n minus 1 times.
N minus 1. Why? Because irrespective of number of inversions, every time we need to compare. When we are inserting second element at second position, we need to compare with first position element whether the condition is true or not. Secondary. First we need to compare. No, we need to compare. Similarly, when we are inserting element at third position, we need to compare with second position. That means for every element, at least, that means when j equal to 2, one time this condition is checked or not? Yes. Correct now? When j equal to 3 also one time this condition is performed. When j equal to 4 also one time, and j equal to n also one time. That means what? Step 4 is repeated, is performed at least this many times. Is this correct? Irrespective of number of inversions, is it performed at least this many times or not? Is that correct? Is there any doubt at this point? Comparison given in step 4, it is performed at least for each value of j at least one time or not? At least one time or not? Is there any doubt in this?
No, sir.
No. So that means step 4 is performed. It is performed at least n minus 1 times. Okay, no? At least n minus 1 times, irrespective of number of inversions is performed. Okay, this many times we can say, at least we can remove now, is performed n minus 1 times. That is same as n minus 1 times, irrespective of number of inversions present. Is that correct? Is that correct? Now, for every inversion, For every inversion, this step is performed how many more times? One more time. One more time. For every inversion, this step is performed one more time. That means how many times this becomes true? How many inversions are there? That many times it is performed. Is that okay? Now you tell me, minimum insertion sort algorithm, minimum step one, it takes n minus 1 time. Step 2, n minus 1. Step 3, n minus 1. Step 4, minimum n greater than or equal to n minus 1 times. N minus 1 times. Okay, no, that okay. Exactly, it is step 4. It is clearly n minus 1 plus what is that we can write? Plus what is that we can write? Plus
Number of inversions.
Number of inversions. Number of inversions. Step 5. Step 5, how many times it is performed? Step 5. Step 5, how many times it is performed?
Same, n minus 1 plus number
No,
of.
no, no. N minus 1 doesn't come, no.
Sorry,
If this is true, then only we come inside, no. If this
number
condition,
of inversions.
it is number of inversion times. Is it clear, sir? Step 5 is performed,
Yes,
number of inversions time. Is that okay? Step 6, it is also number of inversions time. Step 7, we know that it is n minus 1 times only. Now tell me what is total running time of this algorithm? Equals to all these are n minus 1, n minus 1, n minus 1, no? N minus 1. So this 4 n minus 1s we can write plus 1, 2, 3, 7. This is 1, 2, 7 steps. 1, 2, 7. Sorry, not 1, 2, 7. 1, 2, 3, and 7. It is 1, 2, 3, and 7 steps. Is that okay? Plus, now fourth step, how much? N minus 1 plus number of inversions. Fifth step, again number of inversions. So we can say 3 into number of inversions. Is that correct? Is that correct? Is that correct? So overall, we can write it as 5 times n minus 1 plus 3 into number of inversions. Is it okay? 5 times n, sorry, n minus 1, no? Is there any doubt up to this? Is there any doubt? Is there any doubt? Now, what is number of inversions? What is number of inversions? Minimum is
0.
0. Maximum is
N into n minus 1 by 2.
n minus 1 by 2. Now, if I take minimum, then I will get minimum running. We will get minimum running time of this algorithm. If you take maximum, we will get maximum what is worst case running time of this algorithm. If you go for minimum, we'll get best case running time of this algorithm. Is that okay? Okay. So now insertion sort. What is T of n? T of n can be written as 5 times n minus 1 plus 3 into, say f of n is number of inversions. F of n is number of inversions. Now what is best case? What is best case? F of n is how much?
0.
0.
0.
So then what is T of n?
5n minus 1.
Order of growth is
N.
again n. There is no change. Okay. Now worst case. Worst case, what is f of n? N into n minus 1 by 2. N into n, that means maximum number of inversions. No, that is worst case. So what is T of n? 5 into n minus 1 plus 3 into n minus 1 by 2. Is that okay? What is order of growth? n square. Is that okay? Now combiningly, how to represent running time in terms of inversions? Now best case, worst case, explicitly we have derived, and both are same as we discussed earlier. Now how to represent running time in terms of number of inversions, where f of n is number of inversions when array size is n. Combiningly, irrespective of this best case, worst case, only one answer we need to give. That should take care of all cases. Can we say that T of n is maximum of n minus 1 comma f of n, order of growth of T of n is maximum of n minus 1. N minus 1 means n only, no? Maximum of n minus 1 comma f of n, order of growth of maximum of n minus 1 comma f of n. Is that correct? Is that correct? Order of growth of T of n is running time of insertion sort, is order of growth of maximum of n minus 1 comma f of n. Is that correct? Combiningly we are writing so that it will be true for best case as well as worst case. Or can we write it as order of growth of T of n equals to n minus 1 order of growth of n minus 1 plus f of n. Can you say something like this? Order of growth of T of n is order of growth of n minus 1 plus f of n. Is that correct? Is that correct?
Yes, sir.
Yes.
Okay, because we know two quantities. However we want, we can represent. However we want, we can represent. Is that okay? Okay. So next, is there any other way of representing this? Can we say that T of n is always running time of insertion sort? Can we say that T of n is big omega of f of n?
No,
Can
sir.
we say that T of n is big omega of f of n?
No, sir.
Yes,
No,
sir.
it is false.
So T of n, this is correct only, no? It
No,
is
sir. It's big omega, no? So in case of the best case, when inversion is 0,
then T of n is big omega of 1. That is correct only, no?
yeah, correct.
In any case, it is big omega, it will be true for any case. If I write T of n as T of n equal to big O of f of n, it is wrong. This is wrong. Is that clear? Why T of n is big O of f of n is wrong? Not only that, T of n is theta of f of n is also wrong.
Sir, in this case, in worst case, when f of n is order of growth of n square, can we write big omega of n square?
What is which thing you are talking about? First one or
Yeah,
second one or third one?
First one, sir.
That is correct only, no, sir. If number of inverse, if f of n is n into n minus 1 by 2, then T of n is automatically n square, no? T of n is order of growth of T of n is n square only, no?
Yes.
Because this much work we do inside, no, algorithm.
Yes, yes.
But
Understood, understood.
second and the third both are wrong. Is it clear to everyone? Second and third both are wrong. Is it clear to everyone?
Yes, yes, sir.
So now if you please give me an answer for T of n in terms of big O, in terms of big O. Correct answer for T of n in terms of big O.
N square. N square.
Can we write it n square? No, but it should contain number of inversions. Our goal is it should contain f of n, no, in terms of f of n. Otherwise, what is the relation? Without this inversions also we have represented, no, that was over, no. We need to relate this with number of inversions.
So in the worst case analysis, number of
T
inversions.
of n means it should be true for any case. Best case also it should be true. Worst case also it should be true.
Can
Sorry,
we write maximum of n minus 1 and f of n?
Thank you very much, sir. We can write maximum of n minus 1 comma f of n. Is this correct? Is this correct? Any case it will be true. Best case also it is true. Even worst case also it is true or not.
sorry, f of n, worst case analysis, no, for f of n, it
Ah.
is square n into n minus 1 by 2. No, sir.
That time T of n is also n squared, no, sir.
Yeah.
In the best case, f of n is 0. That time T of n is also n. It is satisfying, no?
Okay.
Are you okay? Okay. You give me answer for T of n in terms of theta now.
So same, we need to write maximum of n minus 1 and f of n.
Yeah, same thing also works now. Is this correct? Okay, so last representation without using maximum. Without using maximum. We should not use another comparison. For that, we should not use maximum. Without maximum in terms of f of n. Using big O. Can we write it as f of n, n minus 1 plus f of n? Is this correct? Is that correct? Is that correct? T of n is big O of n minus 1 plus f of n.
Yes, we can write.
We can write no, because when do we actually write something is big O of f of n plus g of n? If we really don't know whose order of growth is higher, f of n's order of growth is more or g of n's order of growth is more, we can simply leave it like this. You must observe in case of BFS and DFS, they write V plus E. That means we don't know how number of vertices is more or number of edges is more in the graph. That's why both, if we write V plus E, whichever is more, that answer it takes care. That becomes order of growth, no? Is that clear?
Inversion and winning time of insertion short is one perspective of analysis, or else the complexity will remain same, right?
Complexity remains same. That is nothing. They are exactly, there is a inversions decide how many times, whether it goes into best case or it goes into worst case.
Yeah, yeah. So I've seen this inversion and running time of insertion sort first time. That's why.
Okay. It's there, sir, in core introduction to algorithms by Thomas H. Coleman, if you refer, no?
Yeah.
It is in fact one exercise problem in that. Okay.
But no, generally it is not a part of syllabus, so we always try to ignore.
Oh, okay, no problem. At least if you understand, no, let us.
Yeah.
If you want, you can teach, no? Huh?
Yeah, now it's fine, sir.
Okay. Shall we move to next topic?
Sure, sir.
Okay. So so far we have seen what are asymptotic notations, what does asymptotic analysis of an algorithm mean, and we have seen what is the general plan for analyzing non-recursive algorithms, general plan for analyzing recursive algorithms. We have seen 2 searching algorithms and 3 sorting algorithms. That's what we have done so far. Whatever we have done, no, our main intention was to analyze only. Someone has given an algorithm, how to analyze that. Next thing is someone has given a problem, how to design an algorithm for that. For that, depending on the type of problem, there are different algorithm design techniques or methods or paradigms in the literature. So one such algorithm design technique is divide and conquer approach. Divide and conquer. So it's an algorithm design technique or paradigm or technique or method, an algorithm design method. Algorithm design method. Or it is also called technique or strategy or something, different names. So what, for example, we are given a problem where input size is say n. Input size is n, but n is very large. Instead of directly solving the problem, on input size n, one way of doing that is you can divide the problem into small problems whose input size is smaller than n. So yeah, input size n is there. Say we have divided that into input size n by b. What is this n by b? Input size. So like this, one more problem we have got, which is a original problem is input size is n, and these are the problems which have come from this problem we have divided into. So that's this, I can call it as subproblems, no, which have come from that problem. So what are they? These are subproblems. So now this is subproblem 1, this is subproblem 2, this is also say size n by b. Next subproblem 3, this is also say size n by b. Like that we have divided into say a number of subproblems. How many subproblems we have divided? A number of subproblems. This is subproblem A, SPA, subproblem A. So what is the advantage of subproblem over original problem? Subproblem input size is what is the advantage of subproblem over original problem?
Size is small.
No, input size is small. Input size is small. That is only n by b. What is b here? What is b? B is a constant. If the constant is greater than, whether b can be 0.5, that is 1 by 2.
No, sir.
No, if b is 1 by 2, then what happens? Subproblem size becomes more than original problem size, no?
Right.
So that is not allowed. Now subproblem size should be less than
N.
n. That means n by b should be always less than n. That means what is the value of b?
Greater than 1.
Of b? It should be always greater than 1, where b is a constant. Is that okay? Say we are given a problem, we need to solve it on input size n. We have divided the problem into small a number of subproblems. What is a here? What is a here? A is also a constant. we have divided the problem into small a number of subproblems. Okay, now we divide the problem into say small a number of subproblems, each of size n by b, each of size n by b, and we are solving this all n by b, a number of subproblems. How do we solve this? Again, we'll check whether n by b value is small or not, reasonably okay or not. N by b is small or not. Size. If it is small, directly we solve it. If it is more, again we divide it into small subproblems. Every time how much quantity? N by b, that reduce it by b quantity. That means recursively we solve all these subproblems. Recursively we solve subproblems. Subproblem. So finally we'll get a solution for subproblem 1 or not. Similarly, say this is solution to subproblem 1. Solution to subproblem 1. Similarly, we'll get solution to subproblem 2. Solution to SP2. Similarly, we'll get solution to SP3. And so on. Finally, we'll get solution to subproblem A. After getting solution to all these subproblems, but what is that we need to do? What is our goal? Our goal is to solve problem whose input size is n. Then we somehow combine the solutions of these subproblems, all the subproblems which you have solved, and combine the solutions and get solution for given problem. What is given problem? What is given problem? What is given problem? Whose input size is? Whose input size is? Whose input size is n? Whose input size is n? Is that clear? The procedure? So we are given a problem whose input size is n. That n is somewhat large value. So instead of directly solving the problem, we divide the problem into, say here, whatever I have taken, we have divided into subproblems, all of same size, say for example. But always it need not be the case. We divide into subproblems, each of size, say for example, n by b. Each of size, say n by b. Okay, n by b. Like that, total how many subproblems we are solving? Total how many subproblems we are solving? How many subproblems we are solving? How many subproblems we are solving?
A number of subproblems.
Okay, and we have recursively solved subproblems and got solution to all subproblems. All subproblems. But what is our goal? We want solution for original problem. No. Then somehow combine the solutions of these subproblems, and get solution to original problem. Solution to original problem. Okay. Then this is our final solution. Final solution, which is nothing but a required solution. Now you tell me what are the steps which are involved here. Here, what is that we are doing here? Here, what is that we are doing here? Given a problem whose input size is n, we are actually dividing that problem into problem whose input size is smaller than n. This step, can we consider it as divide step? Consider it as divide step. Okay. Now, what is that we are doing here? What is that we are doing here? What is that we are doing here? We are in this step. What is that we are doing? We are recursively solving all subproblems. All here, no, we are recursively solving all subproblems. Solving means it is like conquering. Okay, this we call it as conquer step. Conquer step. So what is that we are doing here? Somehow we are, if necessary, okay, no, if necessary, this you will understand, okay, no, when we go for some examples. If necessary, we combine the solutions of these subproblems to get solution for given instance. Solution for given instance. This is called combined step. Now, the moment I said if necessary, that means what? Sometimes it is not required. No, that means this is optional or not. Some problems we do combine part. Some problems there is no combined part at all. Is that clear? And if you follow this way of attacking the problem or solving the problem, this is called divide and conquer method. Why not combine? I think maybe they might have given it is optional. They might have not included. Otherwise, they would have called it as divide, conquer, and combine. Okay. Is it clear? What is that we are doing? Is the approach clear?
Yes, sir.
Okay, thank you, sir. Okay. Now, what is our goal? Our main goal is, if at all you are solving a problem whose input size is n by applying this divide and conquer method, what is the time it takes? All three steps we are performing now. All three steps we are performing. When n is input size, the total time it takes, let us call it as T of n. Let us call it as T of n. The running time of this algorithm, this divide and conquer algorithm, we call it as T of n. Then what is the amount of time it takes? What is value of T of n? T of n is time spent in divide step plus time in conquer step plus time spent in
Combined step.
combined step. Is that okay? Now, what is time spent in divide step? That we don't know. That we don't know. Sometime we spend. Okay, now what that we don't know exactly. That let us denote it as D of n. That means simply they are not divided. No, the problems we need to do some work. Then only the problems are divided into sub-problems. The amount of work we do, that I call it as D of n. What is D of n? When n is input size, amount of work we are doing in divide step. When n is input, that we call it as say D of n. Now you tell me, what is the amount of time we spend in conquer step? What is the amount of time we spend in conquer step? In order to solve a problem whose input size is n, the amount of time required is T of n. Then what is the time we require to solve a problem whose input size is n by b?
A into T of n by b, sir.
At each step it is T of n by b. Like that, how many sub-problems we are solving? How many sub-problems we are solving? A sub-problems. That's why overall it will be, what is the amount of time spent in a conquer step? T of n by b plus T of n by b, like that A times. So can we write it as A times T of n by b? A times T of n by b. Is that correct? Is that correct or not? Is that correct? Or any doubt
Yes.
at this point?
No, sir.
Okay. What is the amount of work we do in combined step? Do we know that? We don't know. But we know that input size is n. That let us call it as C of n. C of n. Okay. Now let f of n equals to say D of n plus C of n. Amount of work we are doing in divide step as well as combined step, that we call it as f of n. So what is this running time of this algorithm now? This can be written as A times T of n by b plus f of n. Is that correct? Is that correct? Is that correct? Okay. But one important point is, what is that? When are we going for dividing the problem into sub-problems? When are we going for dividing the problem into sub-problems?
If the input size is very large.
If it is large, okay, it need not be very, okay, we can call it as large. Input size is large. Okay, not large. So large means how much is that? When do you say that input size n value is large? It varies from problem to problem, that value. Large means from problem to problem it is different. So if n equal to 2, do you consider it as large or not? When n equal to 3, do you consider it as large or not? When n equal to 4, we consider it as large or not? That is subjective, no? Okay. So that's why what we do is, if the input size is large, say if input size is greater than or equal some question mark, this question mark can be 4 or 5 or 2 or 3, or it can be 1 or something like that. If input size is greater than or equal to some value, at least this much, then we go for dividing the problem into sub-problems and conquering and combining their solutions if necessary. Otherwise, what is that we do? Directly we solve the problem without even going for dividing it into subproblems. Is that okay? If n is less than question mark, how to solve this? We don't follow divide and conquer method. We don't follow divide and conquer approach. Directly we solve it. Whatever time it takes, that time we write here. If it is n square, if it is constant, if it is that okay? Is that okay? If it is n. So if the problem size is greater than or equal to some value, then we actually divide the problem into subproblems and conquer subproblems and combine their solutions if necessary to get solution for original problem. If the problem size is small, directly we solve it without actually going for divide and conquer method. Is that clear? Is that clear? Is that clear?
Sir, one question.
Please tell me, madam.
When is this combined step not necessary, sir?
That we will see. For example, I can give answer, but elaborate. We will elaborate on that when we go for that example. For example, binary search, is combined step necessary? No. That is also an example, no, where divide and conquer is applied. There is no combined step at all. In the subarray, whenever you find element, that position that you return, no, we don't actually go for combining and returning the answer, no.
Yes.
In case of quicksort also, we simply call partition procedure. Then array is divided into subarrays. We keep calling partition procedure. Once that is over, we explicitly combining the results of subarrays in order to get solution for original array, their sorted array? No, we are not doing. But in case of merge sort, combining is most important step.
Yes.
Okay, that anyhow we'll see with example. For every whatever example we take, I'll explain you what is the amount of work we do in divide step, conquer step, and combine step. Okay.
Sir, one thing is when we actually go for implementing the problems with the help of divide and conquer, actually it is recursive, right?
Recursive. Okay.
So with the large value of n, generally it gives the stack overflow error.
Yes.
The same problems we can solve iteratively very easily.
That's correct.
Then how this divide and conquer actually implements in the real life?
No, that's what. No, because if you follow this method, that's what this TFN it is going to say that efficient. This running time is going to be very less. Running time is going to be very less.
In parallel execution, we can do divide and conquer.
So if processor is capable to do parallel operations, then it is fine.
But we are not at all talking about parallelism here. Our model of computation is RAM model of computation, and we assume whatever analysis we are doing and we will be doing throughout this course, it is with respect to sequential only. Are you getting that entire algorithms, whatever textbooks we read, no, whatever analysis they do, that is with respect to under the assumption that we follow RAM model computation. For that only this analysis, everything.
Yes, as a simple example, no, factorial of n. If you go with the recursive one, it does not give value for very large. With certain amount of value of n, it will give stack overflow error.
Because that additional recursion means additional space is required.
So that's my question, sir. Here also, when we implement recursive call would be there. So how can we, solve the problems using divide and conquer with large value?
That is only space related issue, no, sir. See, always now our concentration is on estimating the time. We are not giving importance to space. Is that correct?
Yes.
So because that any factorial of a number, all those things there, for example, if I declare it as integer, the whatever is okay, what is the maximum number that it can store? No, yeah, how many bits are allocated for that actual implementation? So only that much large numbers only we can calculate factorial of a number, no?
It's space related issues, but still my question is, when we go for implementation, even there is a space issues, we are not able to apply recursion, on the solution.
No, why both variants are there? No. See,
But at certain value of n, after a particular value of n, the recursion fails to give result.
No, if the recursion fails, maybe if it fails for x, maybe x plus 10 or x plus 20, this also iterative one also fails, no?
No, but for the same value where divide and conquer fails, means recursive solution is fails, the iterative is giving result. Anyways, we will see.
That is implementation issue. Okay, no, that also it depends on the problem, no, sir. For example, if we feel that okay, this up to this n we can easily solve it without even going for dividing the problem into subproblem, even that is fine. That's what, no, this large that we need to decide now. So, but your question, I think, for any value of n, iterative is better than recursive. Is that your question?
Yes.
Maybe, but the amount of time it takes to give answer, no. Definitely, here it will be very much less compared with that. I don't know whether I clarified your doubt or not, but still.
Yeah. We'll see. It's no issue.
Okay.
Sir, one basic question I have here.
Please tell me, brother.
N by B, no, here we are dividing size, input size into N by B. The number of sub problems, is it not equal to B, sir, here?
Next point is that only I'm going to give the relation between A and B. Okay?
Okay.
I'm about to explain that. Okay. Now the question is, we assume that we solve a number of subproblems, and size of each subproblem is n by b. Now, what is the relation between A and B? Whether A can be always less than or equal to B, or A can be greater than B, or A can be equal to B. These are the possibilities, no? These are the possibilities. First of all, what can you say about value of A? Whether it will be greater than or equal to 1 or not? What is A actually? What is A?
Number of subproblems.
Number of subproblems we are solving. Either we need to solve one subproblem or two subproblems or three subproblems. Definitely not 0 subproblems, no? Number of subproblems we will be solving is at least one subproblem. So number of subproblems to be solved. Okay. So that's why A will be definitely greater than or equal to 1. Can we say that A is strictly greater than 1? We cannot say. Sometimes number of subproblems is also maybe 1, like binary search. Number of subproblems we get is 2, but number of subproblems we solve is only 1. We require is only 1. See, what is A here? Number of subproblems that need to be solved. Is that okay? Now, what is the relation between A and B? Okay, I give example. When we go for actually that algorithm, you will observe this. In case of binary search, what is B value, and in case of binary search, what is B value and what is A value? Can you please tell me? B is 2, n becomes n by 2, no? N becomes n by 2. That's why B is 2. How many subproblems we solve? One
subproblem.
Right side. That means what is A? 1. A is 1. In case of merge sort, size roughly, it becomes every time say n by 2. How many subproblems we solve? That means B is 2. In case of merge sort, how many subproblems we solve?
2 subproblems. 2.
That means A equal to 2. In case of Stresson's matrix multiplication, what is in size? N becomes
n by 2.
n by 2. That means B is 2. How many subproblems we solve? 7 subproblems.
Seven subproblems.
That means A equal to 7. Now you tell me, is there any relation between A and B? Here it is A is greater than B. Here A equals to B. Here A is less than B. That means anything is possible. There is no relation at all between A and B. Is that okay? Is that okay?
Yes, sir.
A and B, they are nowhere, not at all related. Not at all related. Is that okay? There is no relation between A and B. But A is strictly greater than or equal to 1. B is strictly, A is greater than, B should be greater than 1. Greater than 1. Why B should be greater than 1? Otherwise, n by B becomes more than
Input size.
More than input size, that is n. More than n. Next question is, okay, so if we follow divide and conquer, this kind of general recurrence relation we get. This is called general divide and conquer recurrence relation. But what is the assumption that we have made here? All subproblems are of size n by b. But practically it need not be the case. Okay, now some situations, different subproblems will have different sizes. Okay, now one may be n by 2, the other one may be n by 4. Like that also is possible. Okay, all those things we'll go for examples. No, that time automatically will come to know. Next question is, what is our next question? T of n is, what is T of n? A times T of n by b plus f of n. When n is greater than or equal to some value, that value it varies from problem to problem. If n is less than that value, it is constant. A constant, or even we don't know, directly we solve whatever it may be. It also varies from that problem to problem. Okay. Now, how to solve this kind of recurrence relations and find its order of growth? Order of growth. That is the question. That is the question. Now let us see. T of n is given. What is T of? What can you say about value of f of n? What can you say about value of f of n? What is, whether f of n can be negative?
No, sir.
No, so it is non-negative. Why? Because amount of work we are doing in divide step and combine step. Definitely it cannot be negative, non-negative function. Non-negative function. Okay. Now whatever T of n is given to us, T of n, can we write it as f of n plus T of n by b? Like that, A times T of n by b. Is this correct? Same T of n, we have written it like this. Is this correct or not? F of n amount of work. Again, this is T of n by b, T of n by b, A times. A times. Is that correct? Is that correct? Is that correct?
Yes, sir, it is correct.
Now, what is T of n by b? T of n equals to A times T of n by b plus f of n. Now, what is T of n by b? Wherever n is there, n by b is substitute. What is that we get? N by b, wherever n is there, n by b plus wherever n is there, n by b. Is that okay? Is that correct? Is that correct?
Yes, sir.
Now, in place of T of n by b, can we replace this? In place of T of n by b? In place of T of n by b.
Yes, we can replace f of
We
n
can
by
put
b.
that. So now what is T of n by b? In place of T of n by b, we are going to replace that with f of n by b, f of n by b plus, this is again A times, this we can write it as, this is same as.
No, I think, sir, that would not be A times, because A are the problems, number of problems, no?
Again it is same, no, A is same, no. See, T of n by b is, no, I have not done anything here. Wherever n is there, n by b I have substituted, that's all. again I will get A times T of n by B square plus F of n by
Why?
B.
No, sir. My question is why we are putting f of n a times.
So that is recursively every time we divide that into a number of subproblems, each of size n by b. If n is n by b, again a number of subproblems, each of size n by b.
Okay, so instead of writing a times, simply we have mentioned here a times arrow, right? It is not actually a multiplied by f of n, right?
Sorry, I could not get.
Sir, f of n, that means to divide problems, number of steps are performed, and then finally a times a subproblems are created.
Like that a time T of n by b, T of n by b, T of n by b.
I understood that a multiplied by f of n times to be performed to divide into two problems. I was understood that way.
No, not like that.
Okay, then clear.
Not like that. So T of n by b, that's why I'm going to replace now. T of n by b, I am replacing with a times T of n by b square plus F of n by b. A times T of n by b square. T of n by b square. Is that okay? Similarly, this side also we can replace. This side also T of n by b we can replace with.
F of n by b by
F of n by b. Again a times T of n by b square. Now what is T of n by b square? Wherever n is there, n by b square. Then what happens? A is there, n is there, n by b square. Already by b is there, plus f of n by b square. Is that okay? Now what is T of n by b square? See, in place of T of n by b, this entire thing we replace with. T of n by b we replace with, this is same as T of n by b, no? Is that okay?
yes.
Okay. Now, what is T of n by b square? What is T of n by b square?
F of n by b cube.
So, okay, I'm going to overhead now. We have understood. F of n by b cube.
B square, sir. There is b square.
Oh, sorry. F of n by b square. No, this one.
Yes.
This
And
is
a subproblems of n by b cube size.
Let me write it below this. Okay. So it is T of n by b cube. Like this a times again T of n by b cube. Is that okay?
Yes.
So similarly, if we expand here also what is that we get? T of n by b cube. T of n by b cube. Here also f of n by b square. This also T of n by b cube. T of n by b cube. It is a times. This also if we expand, this becomes f. This will be T of n by b cube. This also will be T of n by b cube. Is that okay?
Yes.
Now again, what is T of n by b cube? Wherever n is there, n. Okay. Wherever n is there, n by b cube. What is T of n by b cube? Wherever n is there, n by b cube. It becomes n is there, n by b cube. Is that okay?
Yes.
Okay. So only this is f of n by b cube plus T of n by b power 4 a times this is T of n by b power 4. Like this here also this becomes a half. This becomes f and this. Is that okay?
Yes, sir.
We keep doing like this. Here, if I assume that it is true, question mark value is 2, and this question mark value is 2 means here it is 1. Directly, I need constant work. If input size is greater than or equal to 2, I need to repeat it like this. If input size is 1, directly I solve the problem, and the amount of work I require for that is constant or theta of 1 or sigma of 1. All are same. I assume this under this assumption. Okay, under this assumption. That means when n equal to 1, we stop now. There is no further recursion. When n equal to 1, we stop. That is the meaning. No? N equal less than 2 means that is n equal to 1. No? N equals to 1. So now if you observe this, does it look like a tree? Does it look like a tree? Does it look like a tree or not?
Sir.
Yes, sir.
So, and this tree based from this recurrence relation only we got, no? This we call it as recursion tree. Recursive calls made and all that details are shown here. That's all. Okay, no? Details. Okay. Now this I call it as a level 0 in the tree. Root is this we can consider it as a root of this tree. This is level 0. This is level 1. This is level 2. This is level 3. Level 4 and so on. We keep going like this. When does it become 1? All ones we should get. When does it become 1? When does it become
n by b power I is equals to 1.
Thank you very much. N by b power I is
at the level D, if
it is
value
1.
of n by b power d is 1.
That is n at ith level, n by b power I equals
Okay, ith level, that's fine. Yeah, fine.
so that implies what? N equals to b power I. That means I is roughly speaking
Log n.
base b. Here it is exact only, not roughly. That implies n we can n equal to b power I. That means I equal to log n base b. So if we take after going for log n base b number of levels log n base b, that means this is level number log n base b, level number log n base b. We get to t of 1, t of 1, t of 1. That means t of 1 means what is the amount of what is t of n value? It is a constant. Constant means we can call it as theta of 1 or not. Is that okay? Constant means it is same as theta of 1. Now, what is the amount of work we are doing in level 1, level 0? What is, okay, same diagram, whatever is shown here. 1 second. Okay, so this is directly taken from Corman textbook. So whatever I explained up to this, is it clear? F of n, yes, all these things. This is t of 1, which is same as theta of 1. It is t of 1, which is same as theta of 1. Is that okay? Now, what type of tree it is? How many nodes each internal node has? How many children each internal node has? This is internal node. How many children it has? How many children it has?
A children's.
A children. This internal node, how many children?
Again A, sir.
A children. Each internal node has A children. So in this tree, each internal node has A children. Not only that, at level 0, how many number of nodes are there? Number of nodes in level 0? Number of nodes per level.
1.
At level I, say. Here, 1 node. How many nodes are there at level 1? This is level 1 now. This
So
is level 0. This is level number.
A power level.
Level number, this is 0, 1, 2. This is last level. That what is last level? Log n base bth level. Correct now? How many nodes are there at level 1? 0, 1 node. How many nodes are there at level 1? Sorry. How many nodes are there at level 0? 1 node. How many nodes are there at level 1?
3 nodes.
No. How many nodes? This is 1 node.
A nodes.
A nodes.
A nodes, yeah.
A we have explicitly drawn, but it is A times now.
Yeah. So A power L for each level.
That means A nodes. How many number of nodes are there at level 2? There are a nodes at level 1. Each
square.
node of level 1 has again a children. A into A. So how many nodes are there at level 2? A square. How many nodes will be there at level 3? A cube. How many number of nodes are there at level log n base b? A power log n base b. We can generalize. No. This is a power 0. This 1 a power 1. 2a square, 3a cube, log n base b, a power log n base b. Is that okay? Is that okay? This is same
Yes,
as
sir.
n power log a base b. N power log a base b. Is that correct? It is same as n power log a base b.
Correct, sir.
Okay. Now, okay, last 2 minutes I stop. So number of nodes at level I is this. What is the amount of work done at each level? Amount of work done. Work done at level I. This is level number. This is I. Say what is how much work is done at level 0? Only f of n work, no? F of n. What is the amount of work done at level 1? Each node f of n by b. Like that, how many nodes are there?
A into f of n by b.
A into f of n by b. How much work is done at level 2?
A square into f of n by b.
A square into, there are a square number of nodes. Each node f of n by b square. Next level 3, a cube f of n by b cube. And swan level, this level log n base b. Log n base b level a power log n base b into what is the amount of work done? Theta of 1. Is that okay? This is same as n power log a base b into theta of 1, which is same as, can we write it as, what is order of growth? N power log a base b only, no? Can we write it as n power log a base b? Now you sum up the work. So level 0 amount of work is f of n. This f of n, can we write it as a power 0 into f of n by b power 0? Is that wrong? B power 0 is 1. F of n by 1 is f of n only. A power 0 is 1. Is that correct? It is same as a power 1 by b power 1. A square by b square, a cube by b cube. So it is complete A array tree. Whatever you get, we get, no? Complete A array tree. That means what? At level I, how many nodes will be there? A power I nodes. Is that okay? A power I nodes. Now tell me, what is the total amount of work done in this entire recursion tree? What is the total amount of work done at entire recursion tree? What is the work done at level 0? A power 0, f of n by b power 0. Level 1, a power 1, f of n by b power 1. Level 2, a square, f of n by b square. Level 3, a cube, f of n by b cube. Last level, theta of n power log a base b. This is last level. Last level means log n base b level. Now what at log n base b minus 1 level? What is the amount of work done?
A power log n.
Okay. So therefore, what is P of n? Sigma I. Okay. Same whatever is there. I take j equal to 0 to log n base b minus 1. Log n base b minus 1. We can write it as a power j into f of n by b power j. Is that correct? Plus last quantity extra. Plus theta of n power log a base b. Is that correct? That's what is given here. So we'll continue in next class. Okay, I stop.